வந்துட்டீங்க. ஓகே. இது இது எனக்கு இதுக்கு சார்ஜர் இப்ப இருக்கு சார்ஜர்.
ஓகே சார்.
நான் நேத்து நான் யூஸ்வலா என்ன எடுத்துன்னு வரேன். இதுக்கு இல்லையா இப்போ? சார்ஜர் தீந்துட்டான்னு பாக்குறேன். 70% இருக்கு.
வரும்ல சார் 1 hour.
Hello.
Yeah. I'm here. I'm sorry. Yeah. So, is everybody here? Hello, can you please hear me? Hello. 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 Okay. But yeah, I think I can't hear you. So anyway, I think I'll just use the chat.
Hello? Hello?
Hello.
Yeah, can you hear me now?
Yeah.
Okay, that's the problem. Okay,
Yeah.
good. We're all here. Your good friend Naveen here. Okay, so November 8th. Okay, so the final exam week is for us, it's a long week. They say December 21st to December 30th. Okay, although the first week is actually for BSc first year. Okay, so what I really want to do is, see, I'll be I have some family commitment that will keep me away from 23rd to 28th. So I want to have the final submission date for the project on 30th December. No, see, November, sorry. And your final exam on 29th. This is the exam week. November. Yeah. Is that all okay? So for the project, you will have to submit some, we'll tell you what the deliverables are. It'll be code with some runs, with some proof that you've run and output and so on. Additionally, you will have to make a presentation, okay? And that will be on the 30th. Okay? You will submit all the deliverables prior to that. And so you have pretty much 1 to 3 weeks to work on. There'll not be any assignments or anything from yeah. So between 23rd and 28th, I'll not be here, but Diganta will hold fort. And any questions, etc., that you may have in the thick of things, can get his help. Diganta, I'm going to make you co-host, and I want you to share. I don't have the project task thing file.
Yeah. I'll share that one. Yeah.
Yeah, and then I have a few words to say that I will do, and after that you can take over. Yeah.
Yeah. Sure. So, do you mean the file that I was sharing in our meeting before, or?
What?
So you mean the file in which I was writing in our meeting, right?
No. I meant the project task description. Do you have it?
Oh, okay. Yeah. I have it. Yeah. Just a sec.
First share that, and then have to say a few words to set the context
Yeah.
for the folks here. You have to look for it, or
Yeah, I have to look for it a little bit, but like I think I should. I mean, it's there on.
it's on my other laptop. See, my other laptop is conking out, and therefore everything I thought I had put it on this. I mean, I can go to.
Yeah, I have it. Yes.
Okay.
Just a second. Sure.
Not this one. Oh, yes, yes. Yeah, you must have already done this 1 and 2, huh? Which was sign how so you guys done with 1 and 2. So there is. Okay, so there is some issue about scaling. So let's fix that. Okay, so later on. So what you're saying is that you're still having some issues in how to setting up of the scaling thing. So you're still not able to rerun the verification. It is still failing. Is that right? So how about the rest of the folks? Okay, so you you guys are able to figure out the scaling part, huh? No. Are you? Were you able to fix the scaling part? No. Okay, no one is able to. But you all been able to run Reluplex with Marabou, and then run one verification of one of the properties on one of the networks. Shauriyam, you will have to answer. Yeah. With Marabou, you have. Okay. Yeah. Okay. So we will fix that. Okay, we will attend to that. But what I want Diganta to do today is to see there are two tasks here. One is there is one where you will be using, saying we have asked you to implement the node merging abstraction refinement thing. Okay. I don't think we want you to do that as a standalone thing. Okay. What is more interesting is trying to do this Linsim deep poly combination to verify this class of properties called permutation invariance. Okay. Now, what is permutation invariant property? You know the set of properties that are already defined in the paper for those networks, which have already been rerunning. There is this robustness version of each of those properties that you could do that I went through in the class. Okay, that will be one part of the thing that you will be doing the verification. But I think the most interesting and significant part of your project lies in doing this abstraction technique, okay, that implementing that abstraction technique using a Linsim, okay, and possibly deep poly. That's why running deep poly on to verify the existing properties would be a useful thing for you to do. Huh? And this task, implementing this task, will require you to actually do some part of this node merging abstraction, okay, inside that. So rather than have you do this number 4 in a standalone fashion, okay, we are saying, okay, don't bother doing that. So do it as part of this Linsome verification scheme. Okay, I can call it abstraction scheme. That and we, Diganta will be describing. He kind of gave an overview, maybe he gave an overview, not maybe he did give an overview, but not without much detail. But today he will be covering that in some significant detail. Okay, and that will pay attention to that. Okay, and now we will discuss it. Okay, so it'll be detailed enough that all the three subtasks that need to be implemented, that you need to implement in order to complete that, will also be described today. We'll then take an assessment of what you feel about the complexity of the task given the 3 weeks time that you have. Okay, so that will require some implementation, which will really be like kind of gluing together, having some implementation that will glue these tools. Okay, and some of it will be implementing, and then running it on some of the networks which are part of ACAS in order to verify this permutation invariance. What is permutation invariance is something that we'll also discuss. Okay, but you will have to fill in some of the details. But most importantly today, what Diganta will do is to give a detailed description of what this new verification scheme that we will want you to work on. And at the end of this session, okay, we will get your feedback about what you feel about it, and we will make a joint assessment, okay, about what the how complex it is, and then we'll make a decision. Okay, so that's what Diganta will do. So yeah, and then that's it. So yeah, you can take it away. So you can start.
Yeah. Sure. So basically, I'll give you firstly an intuitive overview of this framework, which I had already given before.
It helps to turn that light off. Just one moment. Yeah.
Yeah, so I'll firstly give some intuitive overview of the framework. And then I'll talk about the 3 or 4 main parts of it. And then I'll go into details about each one of these parts. Okay. So the intuitive overview is with the previous sort of split and merge technique that you've seen, they were merging neurons only in one layer, right? What we want to do is we want to merge neurons not only just in one layer, but across multiple layers, right? So for example, if this is your network and I'm not drawing all of the edges in between, but you can imagine there are edges in between, right?
I have questions. Okay, why he was referring to Diganta,
Yeah.
about the node merging abstraction. So there, once you label them as ink and dick, you were merging like-minded nodes in each layer. Okay. So, yeah. Go ahead.
Yeah. So yeah, so you were merging nodes only in each layer. So here instead what we want to do is we want to merge nodes across layers, and also we want to merge them, the resulting node that we will get, we want to make sure that that is in some sense a linear approximation of the behavior of the group of nodes, right? So for example, with this network, we might end up merging all of these nodes into one. We might end up merging, say, these 2 nodes into one, and let's say these 2 nodes into one, right? So now what we will do is with this merge, notice that like there are edges within the nodes which will be there, but also there are edges across, right? So these edges will remain in your abstract network, and the edges that are there within each group is going to go away. So what you're going to end up having is you're going to end up having again 3 inputs, right? And you're going to now have again one output, and the output is also coming from one abstract neuron, right? And again, I'll elaborate on all of these later. You'll have one blue neuron and one green abstract neuron, right? Now, each one of these blue, green, gray neurons, they're supposed to mimic the behavior of this entire sort of network, right? So let's draw the edges of all of between all of these and so on. So there were edges like this, right? So for example, if you look at the gray neuron, it's getting the inputs from here, it's getting this input, it's also getting this input, right? So this gray neuron is going to get input from all 3 of our input edges. Right, okay, so let me maybe move this guy down there. This gray neuron is also getting the output from the blue and green regions. So there will be edges like this as well. Similarly, if you look at the blue and green regions, they are also going to get it. So this neuron would have gotten input from here, here, and here, all 3 of these input nodes. So you would have gotten inputs like this, and you would have gotten inputs like this. Right? So this is what our merged abstract network will now look like. We have gotten rid of this, most of the nodes in this middle layer, and we have replaced with nodes like this form. And each one of these nodes will be a linear approximation of the behavior of these group of neurons. Okay. So let me just draw another example to make it clear. So let's say that again, you have 3 inputs, and let's have 2 hidden layers, this time 4 and 4, let's say. And again, we're always going to have only one output, just like what was the situation with CGAR, right? So now can someone tell me, so let's say that I'm merging this guy, this is the dark green group. Let's say then I'm merging, this is my blue group, and this is my pink group, right? So now can someone tell me what the structure of the abstract network will be, just to make sure that you understand at least intuitively what the merge operation is doing to the structure of the network. There are all of these edges, similarly from here, similarly from here, and there are all edges between, and again all edges over here as well. Okay, so now the abstract network, in the abstract network, how many inputs will there be? Hello?
Yeah, the answer was 3.
Yeah, okay. 3. And then how many abstract neurons will there be? What will those neurons be?
Yeah, the answer was again 3.
3, yeah. So there will be 3, green, blue, and pink, right? So of these 3, which will act as the output neuron?
Yeah, the green one.
Right. So the green one will act as the output neuron, right? And so this will Okay, so there will be green one which will act as the output neuron, and then there will be blue and pink over here. So now can anyone tell me, can anyone tell me what all edges will be there connecting these neurons?
Can you hear me?
Yeah,
Why don't you number the nodes?
right. So let's say that these will be 1, 2, 3, 4, 5, 6.
Yeah, so 4 and 5 will have incoming edges from 1, 2, and 3 each. And-
For which one?
4 and 5, neuron number 4 and 5.
Right, exactly. And then,
And outgoing edges to 6 from both neurons.
right,
And 6 will have an incoming edge from all three, 1 to 3.
right, exactly. So then see, now previously we had 2 hidden layers in fairly complicated structure. Now we have reduced it to something much simpler, right? So this is our abstract network. And again, each one of these neurons, 4, 5, and 6, these will sort of try to linearly approximate the behavior of these group of neurons. So if you look at this group of neurons, this group is actually a function that takes inputs from here, right? Or equivalently, it takes one input from here. And it takes input from here, right? All of these edges are feeding into this green region. And then finally, a single output is feeding out from this green region, right? So this green region can be thought of as a function that takes multiple edges, input through multiple edges, and then feeds output through a single edge, right? The idea is that this resulting green neuron, that this abstract green neuron, is going to be a linear over approximation of the behavior of this green region. Okay. Okay. So any questions so far intuitively? So the idea is,
No questions.
yeah, idea is merge across layers and abstract okay, so these are mainly the 2 elements, right? So now let's go into the details. So how do we do this actually, right? So there are, broadly speaking, sort of 4 steps to this, right? There will be step 1, which will be to split and classify the neurons of your network into increasing and decreasing, right? So this is important because to be able to say that the resulting neuron is going to be a linear over approximation, you'll have to basically find a linear bound and then set it to the bound depending upon whether it's increasing or decreasing or not, right? So this will allow you to over approximate behaviors of neurons. Right? Then we'll come to step 2, which will be so step I had written some step 2, which is something else. Yeah, okay, sure. So step 2 will be actually finding these bounds. Right? So by and I mean or, so I'll go into details of that, don't worry. And then, so this is basically gives us the linear approximation, right? Finding these bounds. Step 3 will involve
Diganta,
yeah,
step 2 will have a sub thing of determining the boundary. No?
yeah. So actually, I think I have.
First have to determine the boundary of that.
Yes. So in fact, this will be our step 2, which is determining the boundary. So by boundary, we mean find these groups.
Groups to merge.
Then step 3 will be to find the bounds for these groups. And then finally, step 4 is to construct the abstract network. And use ReLUplex for verification. Okay. All right. So these are basically the 4 steps. And now I'm going to go into some details about each one of these. And so let's start with step 1. So any questions so far? If you're confused as to why you need step 1, don't worry about it. But I'll say in a moment, and then things should be clearer. But 2, 3, and 4 make sense, right? You're finding the groups that you want to merge, finding the bounds for those groups, and then you're going to construct an abstract network for verification, right? At a high level, does this make sense? Does at least 2, 3, and 4 make sense? 1 might seem a bit out of place, but it is required, and you'll see very soon why. But other than that, is at a high level, do 2, 3, and 4 make sense?
Yeah, I think there is general agreement.
Sure. So now let's go into step 1. What is it and why do we need it? So step 1 is going to basically give you convert your network into an equivalent without an over approximation network, where each neuron is going to be classified as INC or DEC. The question is, why do we need it? See, suppose you have a group that looks something like this, right? Let's say this is a group that you want to merge. And let's say that there are some inputs coming into this group and so on. So there are some inputs coming in like this. Some inputs will be coming in through here. Then there are internal edges like this, right? Maybe even there is an input coming in here. And finally, there is an output going out from here, right? So now, to be able to soundly replace the behavior of this entire group with some linear expression, how do we do it? The way we'll do it is we will try to exploit the fact that each neuron in our network has an INC-DEC classification. So specifically, this output neuron is either going to be INC or it is going to be DEC, right? So let's say it's INC. And the same sort of argument will work if it's DEC. So let's just look at the case when it's INC. So if we know that the output neuron is an increasing neuron, what do we know? We know that if we replace this neuron with anything whose value is greater than whatever the value this neuron produces, right? So in other words, if we replace this neuron with any function that bounds this neuron above, we are sound. That is what INC means, right? So if output of our merge group is INC, then it is sound.
Yeah, it is sound, to prove properties of a certain kind. Okay.
Yeah.
Less than or equal. The output is less than or equal to a certain thing.
Right. So maybe I should make clear a few assumptions
I think
before.
That's clear, because that is
Yeah.
kind of the assumption. Okay. And any property, as we discussed, can in turn be expressed. I mean, it's not a restriction. Okay. But for
Yeah.
conceptual reason, so we can assume that there's a single output, and the property that we want to prove is of the form y less than or equal to some constant. And therefore, any other property which is more complicated, we said that it can be encoded into the thing. Yeah. And that's why, that's where the INC over approximation that preserves, that increases, produces a value at the output that is more than, what the concrete value.
Yeah. So, I mean, I'll just state these three assumptions here. And with these two, we can always do an INC-DEC classification. And like sir was saying, these two are not a very restrictive assumptions at all. Okay, so since we know that this node is an INC type node and that this network has this particular structure and the properties of this particular form, we know that it will be sound to replace the output with any function that bounds the node from above, right? So in particular, if we say this node's output is called y, right? So if we have an upper bound, linear upper bound, and let's say that these blues are xi's, right? x1, x2, x3, x4, x5, and this guy is called y, right? So in particular, if we have an expression or a bound of the form y is less than equal to summation alpha I xi over I plus beta. If we know a linear upper bound of this form, remember this is a linear upper bound of the output of this group in terms of all of the inputs of this group, right? So if we have an upper bound of this form, we can soundly replace the output of this group with just this upper bound expression, right? So in our merged neuron, if we have a merged neuron that instead looks something like this, it's a single neuron, it's going to still have all of these blue edges coming in, right? And it's going to have one green edge going out.
Strictly one more. You need one. No, five. It's fine.
Yeah. X1, X2, X3, X4, X5. And let's say that this green edge is Y prime, right? So then in this abstract neuron, what we're going to do is we are going to set Y prime to be equal to this particular bound. right? And this will be sound. We can do that if this original Y node was ink.
Proving that kind of problem.
So this is clear to everyone, right?
Okay.
Okay. So then, so this is what we can do. So we can set abstract neuron to a linear bound.
Because the challenge is in coming up with the values for all these coefficients. Such that
Yes.
that bound is as tight as possible. And which is
Yes.
where I'm giving a little bit of a punchline, so that Linson. Yeah. Okay.
Right.
It's under your choice as to how you define the boundary, and after that, maybe.
Right. So so this is basically the idea. Okay. So now notice another thing is that in step 1, we're only doing, I want to just make this point also clear. We're only doing an ink deck classification. We are not doing POSNEC. And this is
How it goes for deck.
yeah. So this is something that I claim that you can do. You can actually skip the POSNEC step. So again, your final output of the neuron will be of the network will be always marked as ink because the bound is of an upper bound kind, and you'll be back propagating this ink deck classification, right? So I want to show you the inductive step in which you have one layer for which you have, say, some ink deck classification, right? So you have, say, ink deck. And then let's say that you want to split and like classify, and if required, split this neuron in the next or the previous layer, right?
By the way, Diganta,
Yeah.
you mentioned that if it's a deck node, then you have to bound it from below. Okay.
Yes. If it's a deck node, then all of the previous things, like you just have to, this will be, you have to find a lower bound for it, and then you have to replace Y prime with the lower bound. Right. So now let's say that these edges have, this one has a positive weight, this one is a positive weight, this one is a negative weight, this one is a negative weight, right? So now let's see what the classification of this neuron should be according to this, right? So according to this edge, if you increase the neuron, the value going through this edge will also increase since the weight here is positive, and it will lead to an increase in this neuron, right? So that is a sound direction of movement for this neuron. So according to this edge, you can label this neuron as ink. Similarly, according to this edge, if you increase the value of this neuron, the value going along this edge will decrease, and that will lead to a sound direction of movement for this neuron, since this is a deck neuron, right? So according to this edge, according to the last edge, you can also increase this neuron as an ink neuron. But according to this edge, if you need to decrease the value of this neuron to create a sound movement in the other neuron, right? Because if you increase it, then since this is a positive edge, it leads to an increase, and that goes against the deck classification of this neuron, right? So you'll have to decrease the value of this neuron. That leads to a decrease in the value going along this edge, and that leads to a decrease in the value over here, right? Similarly, according to this edge, also you'll have to decrease the neuron, because that leads to increase in the value going along this edge since it's negative, and that leads to an increase over here, right? So we see that according to the two edges, this neuron must be classified as ink, and according to the other two blue edges, we need to classify this neuron as dead. So what we can do is we can just split this neuron into two. We can have a green neuron and a blue neuron, just as we were splitting before. But notice that here we didn't need to do any pause-next split. So we can split it into two, a green and a blue neuron. We can classify the blue neuron as DEC, the green neuron as ink, and then we collect all of these edges which tell us things should be ink into this green neuron. And we collect all of the edges which tell us that this neuron should have been DEC into the blue neuron, right? And notice that these edges can have mixed, the signs of the weights along these edges can be mixed, right? So it's not like either of these neurons are pause or neck. So we have not done a pause neck classification, but instead directly done an ink DEC classification.
Is this clear? It's kind of a small wrinkle when compared to how it was done in that paper, okay?
Yeah.
Where they were splitting into pause neck 4 different things, and here it is done without doing that. That's clear.
Yeah, and I mean, even if you want to split it into pause neck, that is also fine, but I'm saying that this can be done. Okay, so are there any questions so far? Okay.
Go ahead.
So this is all about step number 1. So now let's come to step number 2, which is perhaps the most critical sort of step here. How do you actually find these groups, right? So let's come to step number 2. So see, the idea is that we want to merge groups of neurons that will sort of have close to linear behavior, right? So if our entire group behaves very close to linear, then merging it is going to lead to less amount of over approximation. If our entire group behaves very far from linear, then merging it is going to lead to a lot of loss in information, right? So we want to find a group which are approximately linear. Right?
Yeah, as a comparison, just to contrast, how was the node merging abstraction? What was the criteria used there? Yeah. So like-minded nodes were what's being merged, because here it makes more semantic sense because of the way that you construct your over approximation is different. It's more semantic. I mean, there you were using max and so on. So here it's a little, we think it's a little bit cleverer. How well this works in practice is something that you will implement and then find out. Yeah.
Hopefully, yeah. So how do we find these approximately linear groups, right? So let's start with the output node of the network. So let's start by trying to find the group of which will contain the output node. Okay. So there will be some layer before that and some layer before that, and maybe let's say an input layer there, right? So what we'll do is first thing we will do before anything else is that we will simulate the network on a bunch of inputs. Right? And when we simulate the network, we will collect values along each node, or to be precise, along the so collect output values. Okay. So this simulation should help us to basically figure out or gauge which of these neurons have close to linear behavior, right? So we're going to use these values that we're collected along each node to sort of estimate how close to linear certain groups of neurons are, right? So then what we're going to do is we're going to greedily try and find the bigger and bigger groups containing this output neuron, let's say, that is going to have closest to linear behavior, right? So we know that we have some set of values for the output neuron. So we have one list of values of the output neuron, and we have similar lists for each one of these neurons, right? So we are going to try and find that list of values which behaves closest to, which if we were to add it to the group, behaves closest to being linear, right? So for example, we will try and find, so let's say that we take each one of these neurons and we will sort of add that to the group.
Just a moment. This is an idea that is completely Diganta's. Okay, but I have, let him describe it, and I have a couple of concerns. Okay, that I will in implementing this. How complex it is. Okay, I will raise that. Okay, Diganta, but go ahead. This is his idea.
Yeah. So I mean, yeah, I don't know if this will pan out or not, but let's.
No, this may be, but the thing is, so it is always, you'll have to figure out, consider all subsets of no. Anyway, describe it, okay, and then maybe my relevant or yeah. Go ahead, please go ahead.
Yeah. So what we're going to do is we're going to sort of add nodes one at a time to the group, trying to see how linear it is. And as long as it's within some tolerance of linearity, we'll keep adding. And as soon as it crosses that tolerance of linearity, we will discard it, right? So for now, let's assume that somehow given a group, we have some way of judging whether or not it is linear, right? So what we are going to do is we are going to look at, okay, which of these neurons, which of the other neurons in the network are most linearly related to these neurons according to the set of values we've collected. So let's say that it's this neuron. So we decide that, okay, this neuron has to be in our group. So now we have a neuron here, and I purposefully chose a neuron in the next layer because now we have a neuron here and we have a neuron here in our group. But if you remember, we need some neuron in the middle layer, right? So now what we're going to do is we're going to look at the middle layer because we need a neuron in the middle layer. We're going to look at the middle layer and among them choose which of these neurons, the input to which of these neurons is, so the input to which of these neurons, so which of these neurons, the values feeding into it, the input to which of these neurons is actually closest to being linearly related to the value seen by these two neurons, right? So let's say that we figure out that this is this neuron. So now we have a group. Sorry.
But here I have a question, Diganta.
Yeah.
Among all other alternatives, okay?
Right.
In order to really close in on this being the best linear approximation that you get, but you would have to consider all other alternatives, no? So that will that, unless you're clever about it, you might end up considering all possible subsets.
No. So that is why I'm saying we'll do it greedily.
That's why you're doing what?
I'm saying that we'll do it greedily. So in particular, what I'm saying is, so maybe let me step back a few steps. So for example, over here, when we're choosing the neuron, the first neuron, what we'll do is we'll look at this neuron, 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 and so on. And for each neuron, we'll see how closely it's linearly connected with this neuron, right? So at this moment, we're only considering two at a time in some sense, right? And we find that this neuron is actually the one that is most closely linearly related to this particular neuron, right?
But what is the, when this neuron is closely related to this means what? I mean,
Yeah. So how do you actually measure, a group of neurons are closely related or not? That I'll come to. Okay, that can be done with SVD. So just so that with singular value decomposition, it can be done. So what SVD will sort of tell you is that given some of these values, it will give you how much it varies along each dimension. So it will give you a vector along which it varies most, and another vector along which it varies less than that, and so on, right?
you guys got it? Yeah. The STD. I'm not sure if everyone got it here. Huh?
Yeah. So I just want to. Okay.
SDD. So you have to explain.
Right. So maybe let me take a detour and explain SVD, then we can come back to this, right? So a detour question or a sub question. So you're given a set of values for a bunch of neurons. So, or let's say that you're given a set of values for the input and output of a group. The question is, how linear is it? Right? So you have sort of, a stack of values, right? So for example, if say this is your group, and there are, let's say, some inputs like this going in, 4 inputs, let's say, and 1 input coming out, right? So now you know that, okay, you're going to have this sort of a stack of values where you're going to have 4 values of input, 1 output. Again, 4 values of input,
Here.
1 output, and so on.
Would it be from a time and doing a top-down approach? Okay, so
Yeah.
it would be good to, although I should have brought this thing up right in the beginning from the thing. Let's suppose that's this step 2. For now, you say you somehow determine the boundary. Okay, explain the rest of the step so that they'll get the top level view, and then come back to this.
Yeah. And I think I'll just spend 2 minutes on step 2 to giving a more high level idea of step 2. Then I'll go on to the next step and come back to it. Okay.
Yeah. So these details are important. So because that's part of the thing. But
Right.
I will let you.
So the basic idea is that you'll have to trust me on the fact that I have, like, there is some way of, given a group, there is some way of saying whether it's linear or not, right?
That part, okay, they can take you for your word.
Right.
How do you know which group?
So even given a set of values, I can tell you whether or not they're linearly related or not, right?
But you will have to look at all subsets of values, no?
So no, we will not look at all subset of values. What we'll do is among all of the neurons in the network, we'll try to find the neuron whose values are closest related to the input neuron, right? And for that, we'll only need to look at all of the neurons once. So that is a linear thing. Right? So
yeah, but that will be for one input.
So that will be for one input. So now we have one input. So now we need to find, we need to actually make the group contain something in the intermediate layer. So we need to do this for the intermediate layer as well. We have one input like this, right? And now we are going to repeat the process. And again, we're going to look at all of the rest of the things that we have not put in the group. We're going to find the one that is closest related to the values of the things which are in the group, right? And we're not looking at all subsets, right? Because we're not looking at combinations. We're only at any given point of time, we're only putting something that is already closest related to the group into the group, right?
Okay, but you can keep doing this. Okay, yes, I agree that you're picking one which is the best. Okay,
Hmm.
but how do you know this is for that you need to enumerate over all the ones that are not yet have not yet been included, correct?
Right.
Okay, so that is first time it'll be n, second time it'll be n minus 1, third time it'll be n minus 2, and so on. Ah.
Yeah, but we're not going to do it until we've sort of exhausted the entire thing. We are only going to do it up until some epsilon. Until we find that okay, the ones that we're seeing so far are not close enough related to the group at all, right?
Yeah,
So
have some kind of a
stopping criterion, yes.
a stopping criteria. And
Yes.
when it gets any worse than that, you stop. Okay.
Exactly. So for example, we might find that okay, we can include this. So then the group expands to being
Like
this.
the lack of precision. I mean, a low bound on the precision, correct?
Right. That stopping criterion will give us a lower bound or an upper bound on the lack of or on the amount of approximation introduced.
Yeah. So this is for one input, but your idea is to do this over some random set of randomly sampled set of inputs, correct?
Yeah, so every time when we are deciding whether or not a neuron is closely related to the existing group, we are using the set of so the values seen via simulation of that neuron.
Yeah, but my question is, you have to repeat this for every input?
No, we don't have to repeat the group building process. We have already done a simulation for say n or some k many inputs. And then we're using the entire stack of values that we've seen so far from the simulation to do the comparisons, to be able to say whether it's linearly related enough or not. So when we're deciding whether or not to, for example, introduce this neuron, we say have let's say capital K many inputs. So we have capital K values here, capital K values here, capital K values in all of these things, and capital K values here, right? So we're using all of these capital K values and comparing it with the capital K number of values we have seen. So we're using all of the inputs. Okay. Yeah.
You're using the entire set in determining for each node.
Okay. Yeah. And that won't so that is not I don't think that will be the computational bottleneck issue. We can vary the size of the set and so on. And SVD is generally speaking fast enough, right? I've done SVD for some hundreds of thousands.
I see.
Yeah.
The SVD thing is supported as some kind of a library routine.
Yeah, it's there in NumPy itself.
Okay.
Yes, the SVD is there. So this finding of this group's code that you'll have to write. And so let's say that once we have found this as the group which will contain the output neuron, then we can select one neuron from the last layer, right? And we can repeat this process. So we'll select this neuron. Let's say this is the most closely related. And this is also close enough related. So let's say this is also close enough related. So then this becomes one group, right? And let's say that these two are in a group of their own. So then we have this sort of an abstract network. right? So this is the high level view of this step. Now, finally, once you have these groups, then how do you find the bounds? That is the step number 3. And this again can be done using Linsin, or using something like Linsin, let me say. I don't know, like not exactly, like you'll not be able to use the Linsin's existing code, but something like Linsin. The algorithm will be like Linsin. So if you remember, what we have right now is we have some group, some arbitrary function, inside of which there is basically something that looks like a neural network only, right? And we are feeding some inputs into it, and we are getting an output out of it, right? So if you look at Linsin, what Linsin does is that Linsin this can get linear upper bounds and lower bounds for any function, right? They were using this for activation functions, but in general, it can do this for any function that will take multiple inputs and give one output, right? So far, this is okay with everyone, right?
You just have to, encode whatever this sub network is doing in terms of a function, correct?
Yeah.
Feed it into Linsin.
Right. So Linsin can handle this network, right? But what does Linsin do to like be able to handle this network? The main, like the way in which Linsin works, if you remember, there was multiple sort of phases, but mainly there were 2 phases, right? So phase number 1 would use LP to find coarse unsound bound. And then step number 2 would use SMT to find sound bound, right? So do you guys remember all of this? And when using LP, they would basically be simulating the function. And when using SMT, they will pass the SMT encoding of the function to SMT, right?
Yes.
No questions so far?
No.
Yeah, sure. So what we can do is, see, we can do sort of the similar thing, but we have an advantage. See, our function.
Diganta,
Yeah.
now, why do you say that they cannot use? Well, the question is, could Linsin be actually used as a black box for this step? I mean, if you could extract the function.
I've looked at their code and I don't think it can be ready. Like it's tied to DeepPoll in a way where I don't know if it can be readily set up as a black box.
Okay. Why? I mean, if it can accept this, it all depends on what Linsin input function. What is the format of the input function? The format that it uses.
So the format it uses is SMT, but
then if this entire network can be modeled as an SMT formula.
No, but their existing code that they have sort of they have this, their existing code is sort of tied into DeepPoll. So the existing code that they have, it is it is sort of a Linsin plus deep poly implementation. So they don't have a standalone Linsin tool that one can use. Their existing code is something that is sitting inside deep poly right now.
Yeah, but I thought Deep Poly uses Linsin as a sub task, no?
Yeah. So it does, but
Black box. I mean, Deep Poly is calling Linsin. It's not the
as a black box, yes. But like what I'm saying is that in their code, while conceptually that is true, in their code they have the way they have actually written their code is by taking deep poly and modifying it so that it can pass data to Linsin, and they have their Linsin module is integrated into that code. So I think cutting the module out of that code into a way where we can use it, that will require some amount of going into the Linsin code and making some changes.
I see. So there is some amount of engineering required here.
There is engineering required here. There will be engineering required in step 2 as well.
Yeah, but see, step 2 engineering is, I mean, that is kind of under a control. But here, so unless we just use LP and SMT and build your own version of Linsin for doing this task.
I think that will be basically fairly straightforward and the easiest way to go about it, because like I'm saying, that has some extra advantages as well, because our function, this uses ReLUs. This is just a ReLU DNN, right? Which means that SMT can be replaced with
ReLUplex.
Yeah, or ReLUplex. Yes. So that will have some advantages in terms of scalability and all as well. And then we can just write these 2 steps, right? So these are the 3 steps involved, and then the step 4 is finally putting it all together. And
step 5.
And pass merge network to Manabu.
With the property that you want to verify.
Yeah. The property is always just going to be an upper bound on the.
Property is already encoded as part of it.
Yeah.
Okay.
Right.
15. Okay. So.
Yeah, so these are the steps involved, and these steps can be done parallelly. So if there is a team of people, they can so one person can do step 1, parallelly another can do step 2 and step 3 and so on. And finally step 4, also the part where you're merging the network and passing it to Manabu, that also can be done parallelly. And then finally some integration needs to be done. So this is a task that can be split up and worked on by multiple people. But yeah, so now I think we can make a decision as to whether we want to do this or not.
Just don't give the punchline out. Okay.
Right.
So
Sorry.
So what do you think? Can you do it single-handedly? No. Okay. So even for a team of 2, suppose are you confident that you can do as pairs? Yeah. Can you make it bigger, smaller?
Me?
Yeah. Just scroll up.
Okay. Is this okay? Hello.
Yeah, you speak up and I'll repeat. Or you could speak into your thing. Yeah.
Yeah, just if you can just keep it here for a while. Thanks.
Yeah.
Yeah, I was saying
Yeah.
step 2, requires a little bit of working the details out. I mean, giving some kind of a pseudo code describing the algorithm.
Step 2. Yeah. Yeah.
Yeah, but that still doesn't require you to get into Linsen. I mean, it requires you to do some SDD thing, right? And requires you to figure out a way to search with these nodes. I mean, to partition these nodes in the right way, correct? That search technique was a little bit not completely clear to me yet. And maybe that needs some clarification. Yeah, and that's what that requires. Any
Yeah. So I mean, I'll yeah, I can write up something in a little bit more detail and send it regarding step 2.
Diganta?
Yeah.
Yeah, so step 2 is the one where we have to also give some sample inputs and look at the neurons, then
Ye-
select from that, right?
Yeah. Yeah.
Yeah, okay.
So step 2 was the one where you do some sample inputs and then you see which is the most linearly related, put that into the group, then make sure that the group is one connected component and so on.
Okay, so you're saying that we give some sample input, then looking at the values of output of each neuron, we run a SVD and
Right.
find, say, correlation or something like that to see which neurons are more connected together.
Exactly. And specifically what I think can be done is if you do an SVD, see if the SVD, if the last singular value is small, then that means that things are linearly dependent on each other, right? They're not independent, right? So that makes sense, right?
Yeah, I got somewhat what we're trying to do. I'm just thinking.
Yeah, but basically, yes, we'll look at the values and then some measure of linearity and use
So
that to.
what you're trying to say is that using SVD, we'll see which linear combination is the one which fits best, right?
Right.
So with the first singular value, we'll find the linear combination which most represents the neural network the best.
No. So for any combination of neurons, if we do SVD on that,
Right.
then that will give us some list of singular values, right? If that list is, if let's say that list is full, that means that in this particular case, these particular neurons are not very linearly related, right? Because if they were linearly related, for example, if they were on a line, then you would have only one singular value. If they were on a plane, you would have only two singular values and so on, right? In general, if they were on a hyperplane, you would have one less, like your last singular value should be 0, right? Um, um, are you there? Hello?
Yeah, Diganta, so it's Rohan.
Yeah.
So can you explain again how we are using SVD to find the?
Yeah, sure. So I'll write something. So basically, that is what I was writing, right? So imagine that you have chosen, you want to give a score as to how linearly related the inputs and outputs are for this group, right?
Mhm.
So you have chosen some inputs, you've got 4 inputs and 1 output, and you have listed them all out into a stack like this, right? Now you'll do SVD on this, and that will give you.
Can you represent the sample inputs, like the different inputs that we've used?
Yeah. So these are coming from the sample input. So remember that these might come from some intermediate nodes themselves.
Mhm.
But yes, they are coming from the sample inputs. Yes. So they're basically result of the simulations in some
Can you
sense.
just wait for a sec? Sir is trying to say something.
Yeah, sure.
Discuss more about the details and so on. Now, given that you have some okay, of things, so let me ask. First, it's kind of a rhetorical question, but it's not. So, you think that you'll be able to do that part will be very fun. That's what I do. So, team of 2 doing in 3 weeks. I think it's what do you think? Yeah, see the step 3, step 2, I think, if we can help out, maybe you can do the implementation. Step 3 is a little bit, I'm worried in the sense because you will have to extract, go under the hood into LinSim. I mean, either you will have to do it from scratch using some of the widgets that is used inside LinSim, or if you cannot use LinSim in a black box fashion, that I'm a little bit worried.
I think
That's
step
more glue-like thing.
right.
Yeah. In any case, this requires some significant effort if you want to produce. So here is a proposal that Diganta and we were thinking. Okay, rather than do it in team of 2, so you make team of 3. Okay, and then since one team you split, merge it with the other. But then each of the 3 people will have to do one task, okay, or some equitable share where we will determine. And
So are people up for it, that they're confident that they can do it? Like,
yeah, the 3rd step you're saying. See, there are one way of reducing the thing is the amount of effort is of course one is splitting the team, so you'll have 3 people. The other is even for a group of 3, doing step 3, how much effort it is something that we'll have to estimate.
hmm.
I mean, I was hoping that you'll be able to do it as use LinSim as a black box. I'm still think, I mean,
I've checked that. I feel that like it's better that an implementation is done than using LinSim as a black box.
Do the implementation, it obviously doing it from scratch will be too much effort. So what is the primitives that you can actually use from inside LinSim? That depends, so you'll they'll at least have to.
No, I think even from scratch, so this is a much simpler version. So then even within Linsen, they were doing a number of other steps and so on to guarantee better tightness and so on, which in a nonlinear setting makes sense. In our case, I think just this is something that we can try. And even if people are worried about step 3, then maybe I can try and give an implementation out of step 3 if people feel like this is the not going to work out. That is also another proposal that like I'm making.
No. Say that again. So I don't think that. So there was a little bit of crosstalk. So what are you proposing? So you could do step 3 and give it to them. Is that what you're saying?
If required. But I mean, I don't think it should be. I don't think that step 3 is, see, like this is, you'll have to just make one LP call, right? And you already have data that is simulating function from step 2 itself, you'll have data. So you have some data, assume that you have some data.
Okay.
You have to make
The
one
essence call, it is iterative, correct? You will have to keep adjusting the thing until you converge, right?
Yeah. So you have to keep adjusting the thing until you converge.
Yeah, that is why I was suggesting, instead of you doing the whole thing, if we could, between us, give them a pseudo code. Okay.
Yeah, definitely. I'll put out a pseudocode for all of these steps. Yes.
Implement it. Yeah.
Yeah. So I'll put out a pseudocode for all of these steps.
Yeah, and that's what I would do. So writing a pseudo code, I guess writing a pseudo code, so in any case, even if you guys, even if you do it, as a first step is, I want you guys to be writing a pseudo code for each of those tasks, okay? And, have it, from on every class, you will concentrate on this.
So yes, if we go about with doing this, I think a good idea would be to decide immediately what the teams are and which person is going to work on which step. So step 1, 2, and 3. Basically, just deciding which person is going to work on step 1, 2, and 3.
Yeah. So
and
I propose that you do it as team of 3. Okay. Because I'm interested that you get something working out of it. Okay. And we will do it as a team. I mean, of course, I always aim a little bit high, ambitious, if you want to call it. So there is, as an attraction, I'm saying, not to put pressure on you. Completely voluntary, also depends on how much progress we'll make and so on. I mean, I haven't spoken to you about this, Diganta, so you could, might be in for a surprise, okay? See, there is, every December, when is the SAT SMT school, Diganta?
I know, sir. I'm trying to come. I've been trying to apply via TCS, and there is some.
I think it's usually happens December 1st week or 2nd week or something.
So this time it is December. So I think this time it is December 17 to 20.
This time it is happening at IIT Madras. Okay?
Yeah.
And there is, that is. Huh? Yeah. Anyway, so you'll have to get it done, for meeting the requirement of the 30th. And then maybe if, good progress, that will be an incentive. So they have a poster session as well as full paper, full session, and especially geared for students. Okay. Students given platform. So in the past, I've always encouraged people, that's why, come this course, okay, when they do the project, and especially those that make very good progress with the project, I've given them the opportunity to maybe do some presentation. So, we could, although we will be doing it as two teams, once you get your part, and then maybe then after that you can collaborate. If indeed they make enough progress, then as a team you could have. That is something on the back of the mind. You don't have to. It's not a requirement or a thing. It's just an incentive, for you to do it. This will certainly be, because it depends on two things. Putting in the effort to get a working implementation is one thing. Whether this will be any better. This is a new idea of abstracting and then doing it. So that is somewhat interest. And if this can definitely, if it turns out that doing this invariant verification, property verification, the traditional Reluplex or Marabou cannot handle it, and you guys, your implementation can handle it, then it might, it is extra incentive, okay, for that, for you to present it. But anyway, so that is aside. So, but let's now get to the thing. So, since we now have gotten this far, we'll have to make the best of it. And I'm not going to be an alarmist, and I think this is doable. And with this effort of having 3 people on a team, and with some assistance on those parts from us in guidance, that you can I think you'll be able to do it, but you will have to put in the effort in doing it in a timely fashion, where you will take the responsibility to keep refining the 3 tasks and working on it, coming back with your feedback and so on. Okay, are you game? Shauriam. Yes, I guess to some extent you have no choice. You got then are you concerned? Huh? You are. You're not. Okay. Okay. So what are the next steps? So you have some class at 3:30. Okay. So then we can end here. So we'll meet again on Thursday. So by Thursday, what is it that we want them to, on our part to do, and what do we want them to do? Okay.
So I have a question. Do you want like pseudocodes of any of these steps or all of these steps from my end? Then I can write it up and send it. Pseudocode?
Step 2. Yeah.
For step 2? Okay, sure. Yeah.
Yeah.
Diganta, this is Rohan.
Yeah.
So we need some elaboration on step 2.
Right.
Right. So for the SVD part, like just what procedure to follow, or what exactly are we trying to do?
Yeah. I'll give you a detailed
That's
write-up
a
on
write-up,
step 2.
okay.
Yeah. I'll give you a detailed write-up on step 2. Yeah.
And for step 3, as sir said, either you could give us a pseudocode, or by Thursday maybe we can look at Limson, and then by the next week, if we can't figure it out, you can maybe give the pseudocode, and for Thursday you could give this SVD write-up. Sure.
So I'll do something. Step 1, there is nothing much there anyway, right? So I'll do a detailed write-up of step 2 and sort of detailed pseudocode for step 3, right? I'll write these 2 things up and send it to you guys.
Step 1 also, in the sense, see, when you have to implement it, there are details that you'll have to work out. Conceptually, it's quite easy. So what's the input? What is it that what is the presentation that you choose? How do you, data structures that you use, and so on. But step 1 is probably the easiest thing.
Yeah. So
step 2, you're asking for a pseudocode.
No.
No? What do you
Step
think?
2, I'm asking for a write-up, from which I can, like, we can understand what he has in mind for using SVD.
That's what I meant.
Yeah, and of course, like if you think that there is some better measure for this thing than SVD or in general some better measure, please.
Okay.
Yeah. Yeah, but I'll write up something in detail for step 2 and I'll send a concrete pseudocode for step.
I
step
think the
3.
what is writing up rather than in English. I mean, I would say that you just write a pseudo. I mean, I keep calling it a pseudocode. So with some steps.
Yeah. When I say detailed write up, I mean pseudocode and explanation.
Yeah, and how about step 3? The one that is the one that I'm a little bit, or even for that, if you could write the pseudocode, and then
Right.
they'll be able to refine it after that. Huh?
Yeah. So I'll do that. I'll do that. So
I mean, but is this too much work for you between now and Thursday?
I'll try and make it happen. At least I'll get one of these 2 things out by Thursday.
No, I think you should do it. I mean, it doesn't have to be a perfect thing. I mean, you just whatever.
Yeah. I'll get at least see step 2.
Let's circulate that.
Yeah.
And each of us, including you guys, will have to review it and then poke holes or ask questions about it. Okay.
Right. If we run into some problems, we can just come back with that.
Yeah.
Okay. Okay, then, of course, we'll have to, I mean, whether you do invariance property. See, the reason for invariance property is, we'll talk about invariance property because that will require, in order to encode the invariance property, you will have to make a copy of that, the network, one full copy of the entire network. That's when you will be doubling the number of nodes, and you will have to end up having to use some kind of node merging or something like that is what our guess is, especially when you want to apply it on ACAS like, reasonably big network. Okay, and that's when the value maybe of this thing, whether it scales to that or not, will be tested in your implementation. Yeah. So let's give it a crack, and then maybe I'm sure even if we succeed 50%, okay, it'll be worth the effort. Yeah. Okay.
Yeah.
Okay. So you quickly, So we'll publish this. I mean, we will put it on Moodle, and you will write something up, Diganta, and then circulate it. Yeah.
Yeah.
And, it doesn't have to be pretty. Yeah. And
Yeah.
complete. So let's find it during our discussion on Thursday. Yeah.
Right. Sure.
Okay. Thank you. Can you?
Yeah. Sorry. I was actually, yeah.